Behind almost every machine that runs smoothly, whether it's your car's engine or a massive turbine at a power plant, there's this unsung hero of engineering. It's called dynamic balancing. It's basically the hidden art of stopping that violent shake before it even has a chance to start.
Oh, you've totally been there. You've just thrown in a load of laundry, but all the heavy, wet towels have shifted to one side. And suddenly, your washing machine sounds like it's trying to break down the door, just vibrating and shaking its way across the floor. Well, that chaotic dance, it's all because of a really simple problem with a surprisingly clever solution: imbalance. So, how in the world do engineers actually tame that chaos? Well, here's what we're going to cover. First, we'll dig into what the problem of imbalance really is. Then, we'll look at two totally different ways to fix it: adding mass versus taking it away. We'll put them head to head, see how engineers decide which way to go, and then, at the end, we'll reveal the one golden rule of physics that ties this whole thing together.
Okay, so what's really going on inside that runaway washing machine or that shaky engine? It all boils down to things being just a little off center.
The official term for it is dynamic imbalance. Now, think about it like this. In a perfect world, an object's center of mass is dead on its axis of rotation. But if one side is even a tiny bit heavier, that center of mass gets pulled away. As soon as that object starts spinning, that extra weight wants to fly outwards, creating this powerful, rhythmic vibration that can literally tear a machine apart. So the whole goal of balancing is to nudge that center of mass right back where it belongs, right on the axis, and make the vibration disappear.
To pull this off, engineers basically have two main philosophies. The first one, let's call it the builder's approach. It's super intuitive. If one side is too heavy, you just add a little bit of weight to the opposite side to even things out. Simple, right? And they do this in some pretty clever ways. Just think about your car's tires. See those little metal blocks clipped onto the rim? That's it. That is dynamic balancing by adding mass. In other cases, engineers might actually bolt or weld on counterweights, use special little balancing screws, or for really fine-tuned jobs, they might even apply a dab of special putty that hardens really fast. It's all about building up the light side to match the heavy side.
Now, the huge advantage of this builder's method is that it's forgiving. It's got an undo button. If you add a little too much weight or you put it in the wrong spot, no big deal. You can just take it off and try again. And most importantly, you haven't permanently damaged the original part, which makes it perfect for making adjustments out in the field. But, and this is a really big but, there's a serious catch. At really high speeds, that little counterweight becomes a tiny projectile. If it's not secured perfectly, it can fly off with a ton of force and cause catastrophic damage. Not only that, but these added parts can sometimes get in the way of airflow, like in a fan, or they can just fall off over time thanks to corrosion or vibrations. And that brings us to the second philosophy, which is the complete opposite. Let's call this one the sculptor's approach. Instead of adding to the light side, you carefully carve away material from the heavy side. The tools for this are way more precise. We're talking about drilling holes to an exact depth, milling away just a paper-thin layer of metal, or punching out little bits of material. It's a subtractive process, kind of like a sculptor chipping away at a block of marble to reveal the perfect shape hiding inside. The beauty of this method is its permanence. Once you've drilled that hole, that mass is gone forever. There is absolutely nothing that can fall off, nothing to corrode, and nothing to block the airflow. What you get is a clean, compact, and incredibly stable solution. It's pretty much perfect for things that spin at insane speeds. But the flip side, of course, is that it's incredibly high stakes. There are no do-overs here. If you drill too deep or you drill in the wrong spot, you can't just put the metal back. You might have just turned a very expensive, very complex part into a piece of scrap metal. And even worse, you could accidentally weaken the component, creating a hidden stress point that could fail later on. So we have two completely different ways of thinking: the flexible builder versus the permanent sculptor. So which one is actually better? Which one wins? Well, the truth is, it's not really about one being better than the other. It's all about using the right tool for the right job. So let's see how they really stack up. When you put them side by side, the trade-offs become super clear. If you want pure, rock-solid stability, the sculptor's method wins, hands down, because it's permanent. But if preserving the original part's strength is your top priority, the builder's approach is much safer. And for precision, well, drilling lets you make unbelievably tiny adjustments, whereas adding mass is kind of limited by the size of the weights you have available. That's why you see them in different applications. Adding mass is great for everyday stuff like tires and fans. Removing it is essential for high-performance parts like motor rotors and crankshafts. You're basically treating flexibility for permanence.
So, here's the key. Engineers don't just pick a favorite method out of a hat. They follow a really logical process that's all about the context of the part they're working with. They pretty much run through a mental checklist. First up, is this a one-off part or are we making millions of them? If it's mass-produced, automated drilling is way faster. Next, is the part fragile? If so, adding weight is safer than risking damage. And a huge one, how fast is this thing gonna spin? Once you get above 10,000 RPM, the risk of a weight flying off is just too great, so removing mass becomes pretty much the only safe choice. But that last point, maximizing the radius, that is so important, it's basically the universal law of balancing. And that brings us to the golden rule. It's this one single principle of physics that applies whether you're adding or removing mass, and it is the absolute key to doing it efficiently. It all comes down to this formula for centrifugal force. Now, don't worry, it's simpler than it looks. That shaking force, F, that's what we're trying to get rid of. It's calculated by multiplying m, the mass of our correction, by r, the radius, which is just how far from the center we make the correction, and omega squared, which is just the rotational speed. Now, engineers can't change the speed, but they have total control over the mass, m, and most importantly, that radius, r. And here is the simple, powerful takeaway from all of this. Because that radius, r, is a direct multiplier in the equation, the farther you move from the center, the more powerful your correction becomes. This means you can use way less mass to get the exact same balancing effect. Working at the outer edge isn't just a good idea, it's always the smartest move. It's more efficient, it's less invasive, and it creates a much more stable and reliable part in the end. So, the next time you see a perfectly smooth running engine or just a quiet ceiling fan, you'll know it's not magic. It's a very deliberate choice between building and sculpting, and it's all governed by a simple, elegant rule of physics. It kind of makes you wonder, doesn't it? What other invisible engineering is out there, just quietly making our world work?